Today I'm going to discuss a little bit more advanced topics of loop optimization. So my talk is going to be surrounded by these four areas. First, I'm going to discuss vectorization technique of loop optimization, then register blocking, and roofline model. To be discussing how we can measure that our code is going to be slow or fast before running. And then finally, I'm going to talk about loop tiling. So vectorization. What do we mean by vectorization? Vectorization is simply the process of processing vectors instead of single values. I mean, we're going to use single instruction, but processing multiple data at the same time, simultaneously. And all modern processors nowadays support vectorization. It means processors have an extra hardware component that allow vector processing. It dramatically improves the performance of our code. Such as there is an option for auto vectorization. So we can switch on auto vectorization at compile time, and then our code is going to be vectorized automatically. But this is not always very successful. There are some of the reasons I'm going to discuss later on. And vectorization has nothing to do with language used. So it can be applied in any other languages like C, C++, C#, or Fortran. So it's not language specific. So there's a simple example over here. We have a serial code. So A of 0 and B of 0, we are fetching from the main memory and adding them up and storing back to C of 0. And the next iteration, A of 1, B of 1, adding them together and storing C of 1. So it goes on like A of 2, 3, 4, 5, so on goes on, so on and so forth. So this is the way data is loading and storing is being happening kind of scalar way of doing computation or processing. But if we apply vectorization, then something is going to happen like this. 8 elements with one instruction of A and 8 elements of B are going to be fetched from the memory, and we're going to adding them up and storing all those 8 elements to C. So if we switch on our auto vectorization, something is going to happen like this. So compiler is going to vectorize automatically our code, and all these 8 elements are going to be fetched and stored automatically simultaneously. So there are 4 main ways we can apply vectorization. So first, auto vectorization, as I have already discussed a little bit, we can switch on O of 3 option, this flag, or at the command line we can add minus FTSLP vectorize, or this one, at least in GCC compiler in Linux. And if we add this flag, this option, then we can see which part of the loop has been vectorized. So there is a print on the screen, and we can see which part of the code have been vectorized. In Visual Studio, there is an option called release mode. So we can, if we switch on release mode, auto vectorize will be switched on. And this solution, however, does not provide the best performance because there are a lot of other issues. For example, the main issue is data dependence. So if your code has data dependence, auto vectorization is not going to be very helpful. And the second way of doing, for example, you cannot apply auto vectorization on your code, or there is no vectorized library. So in that case, we can use OpenMP pragmas. So when we use OpenMP pragmas, OMP provides a set of directives that gives extra information to the compiler to allow automatically vectorize the code, especially loops. So these are built into compiler. We just need to use pragmas to access. And then third way of doing is using intrinsics assembly coded functions. So even better than uh, those two ways of doing vectorization. So it is a kind of function normally we use in our program, but it is assembly coded function. And the last option is we can go to our loop body and directly write the assembly code, but it is a little bit hard to do sometimes. But I think out of these four ways of doing vectorization, mainly 1, 2, and 3 are being used significantly. So auto vectorization, as I have already mentioned, if we switch on O of 3 in the GCC compiler, it's going to automatically optimize our code. GCC, then we can get our source code, then get output as binary, and we can add O of 3. And this flag is going to show us which part of the code is vectorized. If we don't want to use O of 3, then we can enable vectorization manually. At compile time, in the command line, we can include these flags, and it will work as an alternative of O of 3. So this is not always the best way of vectorizing, because there are a lot of issues, the algorithm issues or data dependency. So because of those, O of 3 is not always helpful. OpenMP, the second way of doing vectorization, there's a large number of clauses supported by OpenMP, such as reduction, SIMD, aligned, self-length. So these will allow efficient and easy way of vectorizing, even the loop kernel is more complex. We can see that when we add Pragma OMP SIMD, when I'm writing Pragma OMP SIMD, SIMD is basically going to convert this loop as SIMD loop. And we're adding this clause and saying, telling the compiler that this memory should be aligned. And in the second example, if we look at that, there's a data dependence over here, because there is a data dependence of a distance of 4. So, for example, A of 0 is, so A of 4 is depending on A of 0. And then again, A of 8 is depending on A of 4. So there's a data dependence in this code. And by adding this clause, we are telling the compiler that we need to vectorize the up to 4 iterations. So when we add this clause, it is forcing compiler to vectorize up to 4 iterations. So even there's a data dependence, but auto vectorization in this case is not very helpful. So we have to use OpenMP Pragma and telling the compiler that, okay, there is a data dependence and you can vectorize up to 4 iterations. And the next one is using intrinsic functions, which is like assembly coded function. But the main advantage of using intrinsics, it has portability to almost all 86 architectures, and also compatible with different compilers, Intel, GCC, and others. But there are some downsides as well. So, for example, not all assembly instructions have intrinsic function equivalents, so may not be compatible. But naive way of using intrinsic functions sometimes make the code less efficient than simple serial code, C++ or C code. So there are some problems with using intrinsics as well. So there's a, normally we see that 90% of programs execution time is spent in executing 10% of the code, especially loops. So most of the time, most execution time is spent basically on loops. So rather than optimizing the whole program, there's a better way of analyzing the code using different profilers. So, for example, Intel VTune profiler I have been using a lot, and find out computationally intensive functions. So, what are the bottlenecks in the code? What functions we can find out? Then we can optimize that piece of code, or that just only those functions that are really computationally intensive. So it saves our time and money, but yeah, after that, rewriting loops kernel using SIMD or vector intrinsics is the excellent way, I think. Compilers vectorize the code, not always, but doing that manually using SIMD intrinsics is really a good option, and it boosts up performance. So auto vectorization is not always effective. And vectorization, uh, we can be familiar with a few technologies. First one is MMX technology. This one is very old. It's not being used nowadays. It can handle two floating point numbers and maybe one double number. But SSC, Intel SSC technology, 120-bit register, wide register, that can handle four floats and two double values. And AVX 256-bit wide register that can handle eight floats, eight integers, or four doubles, and 512 AVX technology that can even that has a more wide register. It can deals with 16 single precision floats and 16 integers or eight double values. So I think it's better to check your system, that is which technology your system is supporting, and based on that, you can write your code. But if you can use more than one technology. So, for example, SSC and AVX, you can use both or one. It has backward compatibility, so there's no problem with that. And we can see that this double underscore M256, it is it's like a data type that we declare, like int double M double underscore M128. It deals with single precision floats. But when we declare a variable with this type, we're saying that, okay, we're going to use 128-bit wide register. That means we can initialize four single precision float number. And when we declare a variable with this, we're going to tell that, okay, we can initialize eight single precision float number, and the register is 256 wide, and D is double I is integer, so we can initialize integer double and full. So if SSE 128 wide register can, as I have already mentioned, can deals with four floats, two doubles, and then 16-bit wide. 16-bit wide, we can say 120-bit wide register. It can deal with 16-bit word, and 32-bit double word, and two 64-bit quad word, and so on. And on the other hand, AVX 256 type, it can handle 8 single precision float and 4 double values. So, and another option I haven't mentioned here, AVX 512. Okay, and as I mentioned, the developer can use either SSE or AVX in the code, or both. So both we can use. Some of the load and store vector instructions work only for data. They are written in consecutive memory. So some of them, we need to have consecutive memory locations or addresses in order to use them. Normally, aligned load or store instructions are faster, as you know, than no aligned one. So if memory is aligned, then it is going to be fastest. And but there are some functions we can use for making the memory alive. And there's a Intel website over here, and we can see all of them. Just want to show you all the intrinsics over here. If I, so for example, select SSE technology, a 120-bit wide register, and we can see that store, if we click store, all the functions for storing data is over here. So MMM store PS. PS is packed scalar, single P session flow. Then you can start some load functions for loading, function for storing, yes, function for set. We can assign the values to the variables. So all of them are over here. And you can get all the information how it is going to work, and descriptions and everything. It's very nice. You can see, you can find all the intrinsics functions on the website over here. And then next, a simple example of vectorization. So for example, compiler vectorize such a simple serial code. So we are loading. So without vectorization, what is happening with this loop kernel? We are loading V2 of 0, and then adding this number and storing back to V1 of 0. And every iteration is goes on like that. So this is the serial code without vectorization. If we use SSE technology and 128-bit register, then we're loading 0 to 3. That means we are loading 4 values at a time, and then 4 adding operations together, and then we are storing back 0 to 3, all those 4 values back to V1, 0 to 3. So if we use SSE technology, then 4 values we are fetching from the memory simultaneously at a time, and doing this arithmetic operation and storing back all 4 values simultaneously. This is the vectorized code, but we can see that how we can use AVX or SSE, vector intrinsics. So if we use vector intrinsics, then our code is going to be definitely 4 times faster, because in one instruction, it is fetching all 4 values and doing the computation and storing back all those 4 values. So it's going to be definitely 4 times faster. What we are doing, if we want to use SSE technology, so for example, the vector intrinsics, so we're saying that double underscore M128, that means we're saying that this num1 is 128-bit wide register, and it can store 4 single P session float. So we can use this function mm set ps. It is going to set all these 4 float to num, because our num1 is 120 wide bit register. So it can hold all those 4 floats. And then in our loop, we're using basically incrementing by the factor of 4, because we are using SSE, and it can handle 4 values at a time. So using load ps and fetching all those 4 values from this memory, 0, 1, 2, 3, 4, and storing back to this destination, num2. And doing this computation over here, num1 we have these 4 values, and num2 already we have fetched 4 values from the main memory, and then we are adding them and storing back to this destination, num3. And finally, we are storing back to our memory. So we have this we have this v1 of I, that means 0 to 3, and we have this destination, all those 4 numbers, and we're adding back them, all those 4 locations, these 4 elements, all those 4 locations. So this code is 4 times faster than the serial code. So this is how we can use intrinsic functions. That is basically, it looks like assembly coded function. And yes, I have already mentioned, but it's further a detailed explanation over here. So this is telling that, okay, we can variables of type float and 128 bits can contain four floating point values. We are initializing all those four float numbers to these variables that I have already declared over here, and four iterations are processed in every iteration. That means we are processing incrementing iterations by the factor of 4, and then load 128 bit of data starting from the memory address of memory address of whatever memory address. So we're storing all those four values at this memory address and adding them and storing back to the memory. And okay, so yeah, I just want to mention one thing. What happens if the value of m is 10? Is that code still going to work? Yeah, so if the value of m is 10, the code is not going to work because we are processing multiple of 4. So we are processing 4 elements at a time. So if the value is 10, then we can process first 4 elements in first iteration, and then second iteration we can do first 4 iteration we can do vectorize, and then again another 4 iteration we can do vectorize, and other 2 iterations we can deal with serially. We can process data serially. So this is something called padding code. So we can use this padding code because it's not going to work because we are just processing multiple of 4. So rest of the 2 iterations we have to deal with just serially. So something we can have in our application like this. So we need to always think of which technology we're using. So for example, if I use a VX256, then we are dealing with 8, factor of 8. So 8 iterations at a time. And then again, another 8 iterations. So in that case, so a multiple of 8, we need multiple of 8 if we use a VX256 technology. So always you need to think of what technology we're using and what is the upper bound of this loop. And this is how we can write our code, like padding code for the serial processing. Okay, so this is there are some more, but this is all what I have figured out for vectorization. Like we can do 4 ways of vectorization. So auto vectorization. If we think that our code has data dependencies, then we can use OpenMP or vector intrinsics is the best option. It really boosts the performance of our code. So we can developers can manually write the code and optimize rather than switching on auto vectorization. That will not always be helpful. And next, register blocking is another loop optimization technique. So also known as loop unroll and jam. But this is the main aim of register blocking, using register blocking for our loop is it is very good for increasing register exploitation, meaning that we can reuse the data. So we can keep our data in the register and reuse them. And it also reduces load storing instructions, which is very effective for boosting performance. Also reduce the memory accesses as well. So this register blocking. This is another optimization technique, but it's very, very effective. So there are two. Basically, register blocking is a combination of 2 transformations. One is loop unroll and scalar replacement. So we have to follow the 2 steps in order to do register blocking, implement the register blocking technique for loop optimization. So for example, if we turn on GCC compiler, OAuth3 has register blocking option is enabled, but we can also do something like this on the command line, flop unroll and jam. that will work as well as alternative of O of 3. If we only focus on register blocking, then we can turn on this flag. But I would say a manual application of an is always better. So experienced developer can achieve better results if we if we use register blocking manually rather than switching on the auto optimization. And register blocking, how we can do that? There are two steps. So this is our serial code. We have 3 loops and one matrix, matrix A and matrix B. So two matrices we are multiplying and storing the result to C. But how we can deal with, because this is a slow code, because n to the power 3 times this one is fetching from the main memory, this one is fetching from the main memory, and then store is happening as well. So again and again we're fetching data from the main memory, and which is not efficient. So how we can optimize this code? The first step, we can unroll the loop, not the innermost loop, but the second loop we can unroll by the factor of 2. And when we do that, we can get common array reference. So common array reference is exposed. Suppose this one, A of ik. And also we can get over here as well something that is not depending on the innermost loop. So this is giving, so loop unroll is giving us scope to taking this out of this innermost loop and use register. We can also replace this scalar with a variable in the register, and we can use register. So the second step is to scalar replacement. How we can do that? So yeah, we can take if I look at this common array reference, we can initialize this array to a variable A, and we can use them 2 times. So it means we are not fetching again, we're just fetching data from main memory once, and then we're using this variable. So that means we're not going to again fetch data from the main memory, which is very expensive. Data trafficking and bandwidth, all of the issues, we can use them easily. So it is going to boost the performance. And then as C of ij is not depending on these innermost loop, so we can get them out as well and initialize to a variable C and 1. And we can use, it looks like it is fetching now n to the power 2, but before it was fetching n to the power 3 times. And yeah, so this is definitely going to boost the performance, because load is going to be minimized and boosting performance. So the key point is another key point I want to mention. So for example, we have used a factor of 2, but we can do factor of 4, say for example. But in this case, we are going to get more variables, and the register pressure is going to go high. So that's why in the next slide, this slide, I'm just basically highlighting the number of variables in the loop kernel must be lower or equal to the number of available registers. So we have to be very careful when we unroll the loop. We need to think of our register. So we have to be careful about register size. So what are the number of register we have? And then we can unroll the loop. So what happens if I have more variables in the loop body, then maybe it is overflowing the register, which is called the register spills. Then data is going to be sitting in L1 data cache or L2 or main memory. In that case, data is going to be fetched from L1, L2 or main memory, and the performance is going to be degraded. So when we unroll our loop, we have to be careful that the loop body, the variables are not going to, we're using in the loop, it's not going to be more than the available registers. So if we do that more, if we unroll more by factor of 4, 8, 10, the register pressure is going to high, and then register spills is going to happen. What I have mentioned, I'm going to explain this. So for example, we have unroll factor of 4, and we have more variables because we have common arrays, and we can take them out and store in the variable, and we can use them as register, We can see that register variables are increasing. So if it is factor of 8, then 8 are going to be here. So we are going to 8 variables in the register, but we have to be careful that they are going to fit in the register or not. So if we look at this, before a of ik is loaded and used 4 times over here, we are fetching once and using 4 times, which is very good. Therefore, aijk is loaded 4 times less than before. Here, it was loading 4 times, but now it is 4 times less. Even in your serial code is moved 4 times. Now is 4 times less. So as we know that every load from L1 data cache is more than one cycle, one of the 3 cycles. So it is definitely a saving cycle. And in the first case, so for example, for this, see what is happening here. In the first case, over here, it is loaded n to the power 3 times. It could be, I don't know, depending on the numbers, n to the power 3. Now, when we take them out of this innermost loop, and it is going to be n to the power 2 times. So definitely it's loading less than before. So what is happening now? Register hold the data results, and therefore load and stored are going to be less. Not from DL1, it is using from register, not fetching from DL1. So definitely is going to be useful. And now C arrays references are outside the K loop, and therefore this is definitely n square time, as I mentioned. It is definitely boosting performance. The benefit of register blocking, as already we can see that it is minimizing load and store. So it is minimizing basically the data transaction and bandwidth between main memory and CPU. Not only main memory, but L3, L2, and L1 cache as well. So apart from this, there is another benefit of using register blocking on this code here. It is also minimizing the number of arithmetical instructions. So for example, we can see here that every time arithmetical instruction is reduced to as a less address computation is happening. Before it was different memory addresses used for each load and instruction. So it is computing the memory address as well alongside the load and store. Now, as load store are minimized, so with that, the register we're using registers instead. So less memory is load stored. So and less memory is going to be less memory addresses are going to be computed as well. So this is another benefit as well, that we are dealing with less memory address computations. So this is another benefit of using register blocking. Also, this is another idea we can apply. So for example, we have seen that before, vectorization using intrinsics, vector intrinsics, or simply intrinsics. Now we can combine, we can use register blocking with vector intrinsics. And this is gonna be more beneficial. We can see on this code, we are unrolling the factor up to and doing this, and we're reusing these variables again in the loop body. So it means we're not fetching data from the main memory, but we're using this memory from the register rather than going to get data from the slowest main memory. So this is so vectorization is already effective. On top of that, if we apply register blocking, it's going to be more faster, more beneficial. So this is what we can do as well with register blocking. Okay, so vectorization and register blocking we have finished, and we have seen that already there are a lot of benefits of using them in terms of optimizing performance. Now I would like to shed light on a roofline model. Before running the program, uh, if we can know that how fast or how slow our application is going to be, that is nice as well. So we can measure we can get some kind of idea from this model. The roofline model is basically an easy way to get performance bound, compute bound, and memory bound loop kernels. Okay, I'm going to focus on what is compute bound and what is a memory bound loop kernels, but it allows us to know how far the ASIP performance is from our optimum performance. That means the optimum performance we can gain and how far we are. So that kind of giving some sort of idea. And from there, we can decide that we need to optimize memory bound. If it is memory bound, if it is compute bound, we can decide what kind of optimization technique we can apply and get the code performance better. So it's based on basically the computational intensity, sometimes also called arithmetic or operational intensity. But the formula is in order to get AI, AI is not artificial intelligence. Here in this context is arithmetical intensity. So arithmetical intensity is a floating point arithmetical instructions divide total floating point arithmetical instructions divided by number of bytes load and stored. So I just want to go to another slide to explain this. If we look at these three loops, we can see here that arithmetical floating point, if we think that we are using just floating point numbers, but how many arithmetical floating point arithmetical instructions here? 1 and 2. So we have two arithmetical instructions. How many loads over here? We have three loads because plus equals is going Cij plus then A of I k and B of I in k I j. Yeah, so we have three loads. So each load is loading 4 bytes because we are loading floating points, single precision floating point. This is loading 4 bytes, A of I k loading 4 bytes, another C over here, I j is loading 4 bytes and is storing 4 bytes. So 12 bytes we are loading and 4 bytes we are storing. So altogether 16 bytes. So if we use this formula, it's going to be like floating point arithmetical operations, and we have 16 bytes. So this is giving us sort of 1/8 arithmetical intensity AI. So this is how we can calculate arithmetical intensity. This is based on computational intensity or arithmetical intensity, but we can get our AI using this formula. However, this model has several limitations, like ignore integer computations. But nowadays, we can see Intel Advisor is nowadays has an extension of it for integers. So you can get more information over here about a roofline model. So if the algorithms that have a low arithmetical intensity, it means memory bound. If load store is more, and then floating point arithmetical operation is less, then code is going to be memory bound because we are having more load and store. Data transactions is very high. But the algorithm, if the algorithm that have a high arithmetical intensity, that means arithmetical operations are more being dealt with. So then this the code is going to be compute bound code. So Memory bound means the performance is bounded on memory because obviously we are loading and storing more than the computations. And it depends on latency and bandwidth values. Bandwidth values is data traffic is very high and data transaction is very high. So thereby latency is going to be high as well. So if we look at this, graph, we can see that y-axis is floating point operations per second, and this is x-axis is representing arithmetic intensity. So this segment, there's a critical point over here, but we can see that this segment, this is sort of a linear way of moving. So this box is problem with the memory bound because we can see that AI is very low, but it is increasing, and touching to the critical point. So maximum we can get this mass performance. But over here, our code is performing up to this point, is not fully achieving up to this point. So still we have compute bound problems and memory bound problems as well. That means there is a gap between these two lines. So what it indicates that we have compute bound problems as well in our code. So we can work on our code to optimize in order to get the optimum performance. So it is giving me a good idea that where we are now in terms of performance of the code, and we can think that what we can work on to optimize the code, whether I need to work on memory bound segment and how much we can work with compute bound segment. I can see that flops, how we can calculate this function peak floating point performance, and then another argument is peak memory bandwidth times AI. So peak memory performance is the maximum we can get. So maximum performance we can get as it refers to compute bound loop kernels with a perfect balance between simple and complex operations. So in order to get the memory bound code performance, you can see here that the peak memory bound bandwidth basically depends on DDR memory. Another hardware memory controller hardware characteristics. So it depends on basically the DDR and this. What happens if we can fit our data in the cache? But this is the default, like a memory bandwidth, peak memory bandwidth depends on DDR memory. But what happens if we can keep our data in the cache? Then peak memory bandwidth is going to be the cache bandwidth. And at that point, we can improve the performance as well. If we look at, okay, already I have explained how we can get the AI arithmetical intensity of the code. So we can calculate this way. So total arithmetical floating point operations divided by how much load and store, total load and store. And we can calculate the AI this way. So for example, over here, arithmetical intensity of MMI is 2. We have 2 arithmetic operations over here, floating point arithmetical operations, and 3 loads and 1 store. That is giving me byte. We are loading 4 bytes, 4 bytes, 4 bytes, and 4 bytes store. So 16 bytes. That's how we can calculate 1 by 8 is our AI. Assume that performance is not affected by integer operations. Yes, so because we are dealing with floating points. But if the peak memory bandwidth, suppose 21 gigabytes per second, from then maximum performance of MMM, matrix matrix multiplication, performance will be this. This is the formula we can use for getting the maximum performance. So the bandwidth, exactly this formula is over here, peak memory bandwidth times AI. Peak memory bandwidth, if peak memory bandwidth is 21 gigabytes per second, and then AI of this code is 1 by 8, then maximum performance we can get 2.65 gigaflops. So you can calculate a maximum performance, how much maximum performance we can gain, and we can use this formula to calculate. If the arrays fit in the previous cache memories, then the memory bandwidth is higher, and thus performance is increased. That means rather than keeping fetching data from the main memory, DDR memory, somehow if we can optimize and keep the data in cache memory, then the bandwidth is going to be higher and performance is increasing. So using this model, we can, it's very useful because it can give us an idea of how fast or how slow our program will perform before we run it. And a simple example, Roofline model. This is from Intel Advisor. We can see this red dot. So red dot is basically the indicates the loop kernel that takes a large part of overall execution time. So this is taking more time, but the yellow one is like significant amount of execution time is taking the loop kernel, and then green one is okay. But if we look at carefully with this red dot, we can see that DRAM bandwidth bound. So it means the load and store is happening basically from DRAM. So performance, that's why it is taking more time to execution time is very high. And how we can improve? Our aim is to move this red dot up. It is now DRAM bound, but if we want to move it to the L3, L2, or L1 or up, then we can think that's a roofline model is very useful. It is giving a sort of idea where we are now in terms of performance and what we can do to go further up. So yeah, if we keep our data somehow in L3 or L2 or L1 cache by applying optimization techniques that I have already discussed, and I'm going to discuss another one. So then this red dot can go high and the performance is going to be improved. So we can think of that what optimization we can use. I can see that another optimization, the final one I'm going to discuss is called loop tiling. So yeah, so using loop tiling, we can maybe, or register blocking, we can use more data from register, or L3, L2, or L1 cache, we can use loop tiling techniques or sub-blocking techniques so that we can keep the data in the cache and fetch data from the cache, the nearest memory, fastest and nearest memory, rather than fetching data from the DRAM, the slowest and expensive memory. So loop tiling. So I'm going to go to the, I'm coming back later on this figure, but we can see that instead of processing data, like, so for example, this matrix, and we have a row and column, but if this row is very larger than the cache, like this is not going to be fitting in the cache, even the column as well. So in that case, if we think that it's not fitting in the cache, then we can create some sub blocks. So we can create partitions, loop tiling partitions, that we can partition the iteration space and create some sub blocks. Then we can take each sub block, each tile, and within that tile, the elements in the tile, then at the time that can fit. Maybe all these 6 cannot fit in the cache, but 2 of them can fit in the cache. So that's the idea of loop tiling. So basically keeping the data in the cache. I'm going to further explain how we can do that. From some theoretical point of view, loop tiling partitions a loop's iteration space into smaller chunks. As I shown here, we are creating some smaller chunks or blocks so as to help the data remain in the cache, as I said. So we can reuse the data. That's the idea. The partition of loop space leads partitioning the large arrays into smaller blocks. That's how I have, so that we can fit them in the cache and reuse them. So thereby enhancing cache reuses and reducing cache misses as well. So it is applied to each iterator multiple times. So so for example, J and I iterator in previous examples, I and J iterators. So iteration in previous example, yes. Loop. So this is one of the most performance critical transformations, memory bound algorithm, especially when you see that the code is memory bound, then we can use this technique and boost our performance. Yeah, in data dominant algorithm, the loop tiling is applied to exploit data locality. So for example, in memory, it optimizes the memory bound algorithm. Definitely performance is bound on, so for example, memory hierarchy. Memory is going to be slow and CPU is fast. So arrays take a longer time to be loaded from the main memory to the cache and the CPU. So array can fit in the cache and program faster. Applying the loop tiling is very useful in that case. So, but array does not, if array does not fit, as I mentioned, and remain in the fast cache. So, if array does not fit in and remain in the cache, then we can think of loop tiling techniques to apply. It definitely reduces the cache misses. This does not entail performance improvement at all times, but this technique itself is not always giving us best performance, but it depends on different other factors as well. So, for example, number of instructions and others, but at least it can boost some performance. I'm going to discuss a little bit later on more. So key point here is selection of the tile size. So how many tiles, how many blocks we can use. If it is more blocks, then what's going to happen? Less blocks. So that kind of calculation we need to do as well. Loops or iteration to be applied. How many loops and iterations we can use, that we have to take into consideration as well. How many levels of tile to apply? So for example, multi-level cache hierarchy, we have to keep in mind as well. Yeah, the advantage is increased locality and data reduce cache misses if we use this technique. But the downside is that increases number of instructions. So adding extra loop because of the tile, we are creating tiles, and within the tiles we have to use the elements in the tiles. So where you going to use extra instructions and extra loops. So that is the downside, demerits of using loop tiling. We can see this over here. Several examples. We have three arrays. In this matrix of A, we have row, and matrix of B, we have column. So row times column. And if we look at this loops, more than 2,000, n equals more than 2,000, and the same, basically the same example I'm using again and again. So if we want to do this computation, we are multiplying this row with this column and storing data to C. But in the second iteration, if I want to do the operation, then I need second column for the same row again I need to use. But what happens if this row does not fit in the cache? So cache is 8 bytes. If it is more than 8 bytes, cache is 8 bytes, more than 8 bytes. So for example, is larger this row more than the cache, then the next iteration we cannot use the row. So we have to fetch data from the main memory or L2 cache or main memory, because we can see that all these elements are stored in the main memory, coming from main memory. In that case, so performance is being degraded because of this, because we're not able to use reuse the data. So how we can manage this? How we can keep the data in the cache? So yeah, already I have explained. If A cannot remain in the D1 cache, then loaded from this amount of time loaded from main memory. A cannot remain in L2, then main memory as L2, then main memory. B is same. So a single, if we consider, so for example, single level cache, A array is loaded 2048 times from main memory. So to the power 3 times loads, and B is doing same. B is doing the same. For the columns, it is same happening, 2048 to the power 3 times load. And store is 2048 square stores. So we are loading and storing a large amount, more times. We can see how many times from the main memory. That's definitely the code is going to be slow. There are a lot of data traffic transactions and a bandwidth problem. We cannot reuse, but we want to reuse the data, and then code is going to be faster. So in this case, we can use this technique, loop tiling. So loop tiling, we can decide that, okay, we can use loop tiling. This outer 3 loops is going to basically going to which tiles to multiply. Is giving me the tiles, and the next 3 loops is going to give me the elements within this tile. So now we have this tile and we have this tile. So we have a small row, a smaller row, and a smaller columns. If we take this block, sub block, and sub block, so sub block row, sub block column, we are doing fast, and the next column, and still we are getting this row in the cache. So straightaway we can use this data from the cache. So data reuse is happening over here. It is not overflowing or not fitting in the L1 cache. It is fitting in the L1 cache. So the matrix are partitioned into smaller sub matrix, as I explained, sub matrix, and instead of multiplying A by B, their tiles are multiplied, and the sub blocks, we are basically array is loaded total length by number of tiles. So we are partitioning into tiles, so creating more tiles and taking each tile and processing. Now, after tiling, it is loads from main memory. Before tiling, it was loading 204 to the power 3, B 204 to the power 3, and storing twice. So total main memory access was this amount. After tiling, we are doing 2048 divided by tiles, number of tiles. But we need to think of how many tiles we can use, as I mentioned before. And then we can see that loads from the main memory are going to be reduced. So 3 times 204 to the power 48 to the power 3 divided by number of tiles, main memory access is going to be reduced. So by increasing the tile numbers, performance is increased. However, tile number is bound into the cache I have run this run that program in my machine, and I can see that with no tiling, we're getting 3.9 gigaflops, but tile size is 2048. It's definitely the number of total length, but it is a little bit less performing than the no tiles, because that's why I said number of tiles affect, sorry, number the tile size gives slightly lower, slower code. So we have to think of how many tiles, the tiles we can use. Tile size when you think of as well, yes. But when tile size is 1024 is a little bit higher performance. 512 is more, 256. And then we can see that as tile size is 16, we're getting the best performance. But again, tile size is 8, tile size is less, but still we're getting slower. And why is this happening? But anyway, we can see some performance improvement here. But depending on the tile size, loops, how many loops we are using, so all sort of factors are affecting basically. But why is this happening? We have to take into consideration another thing over here, because it is not the best. Loop tiling is this way of improving performance is not the best, because when we are dividing into tiles, the memory is not going to be stored consecutively. First row of this tile, and then memory is going to be stored from over here instead of along this line. So the memory is sort of randomly placed. It is not in a consecutive memory location. So this is, if memory is not aligned, that definitely randomly placed, so performance is going to be degraded. So this is the issue. So how we can maybe we can use like lot of tiles, so we can use another technique called array copying along with loop tiling, so it may give us more performance if we apply array copying with loop tiling. So yeah, finally, roofline analysis. I showed you before this red dot was DRAM bound, but after using loop tiling technique and keeping the data in the cache, we have improved the performance. Now is red dot is over here, so it's L2 bound like bandwidth. So data is being fetched from now L2 level 2 cache. So this performance is improved because although memory bound, it depends on the cache performance. Now it is faster after using loop tiling techniques. Further reading, we can get some important information on this link. I think that's the end.